Welcome to The Explainer. Today we're diving into the world of digital forensics to uncover how cybersecurity experts catch malicious software that's literally designed to be invisible.
So, here's the big question, right? How do you actually find something that doesn't want to be found? This is, without a doubt, the central challenge facing cybersecurity today. Malware has become a true master of disguise, and a lot of our traditional methods are really struggling to keep up.
To really get why this is such a tough problem, we first need to look at the old way of doing things. For decades, the hunt for malware pretty much started and ended with the file itself, that little icon you double-click on your desktop.
So, traditional antivirus software uses what's called static detection. Honestly, it's a bit like trying to identify a criminal based on their outfit alone. It scans the file on your disk and just asks, what does this look like? But here's the problem. Modern malware can change its outfit constantly.
And believe me, malware authors have a deep bag of tricks for this. They use tools called packers to basically shrink and encrypt their code, locking it up tight in a box. Then they use something called obfuscation to scramble the code, making it look like complete gibberish. The infamous Amade Trojan, for example, it puts its code in a box that's inside another box, using layer after layer of encoding to hide. And what this all means is that when an antivirus program scans the file, it just can't see the real danger lurking inside.
Okay, so if the file is just a disguise, where do we find the truth? Well, the answer isn't on your hard drive. It's inside your computer's active memory.
And that brings us to a core principle in modern cybersecurity, a saying you'll hear a lot: runtime doesn't lie. See, no matter how well a program is disguised as a file, to actually run and do its damage, it has to reveal its true code and its true intentions in memory. It has no choice. This is the whole idea behind memory analysis. Instead of just looking at the file, investigators scan the computer's live memory, its RAM. This technique completely sidesteps all those clever file-based disguises because it catches the malware red-handed right after it has unpacked and unencrypted itself to get down to business.
But, scanning all of a computer's memory is like searching for a needle in a haystack the size of a mountain. So how do investigators even know what they're looking for? Well, it turns out that all malware, no matter how clever it is, leaves behind these unavoidable fingerprints.
In the biz, these are called execution invariants. You can think of them as the malware's permanent, unchangeable digital fingerprints. They are essential pieces of code or data that a specific malware family has to use to work. No matter how much it changes its disguise on the outside, these fingerprints on the inside, they always stay the same. And with a piece of malware like Amade, we know exactly what these fingerprints look like. When it runs, it leaves behind all these little telltale signs in memory. There's a leftover file path from when it was being developed, the specific 32-character keys it uses to decrypt things, and even unique sequences of machine code for its most important functions. These are the clues it just can't get rid of.
Now, trying to find these tiny fingerprints manually across gigabytes of memory would be, well, impossible. So, of course, experts use some really powerful automated tools to do the hunting for them.
The main tool for this job is something called Yara. You can think of it like a search dog for malicious code. An analyst creates a rule that describes the fingerprint they're looking for. They point Yara at a target, like a big dump of a computer's memory, and Yara tells them if it gets a match. It's that simple and that powerful.
And this isn't just theory, okay? Security researchers are constantly sharing scripts on platforms like GitHub that automate this whole process. With just a few commands, these tools can download hundreds of known malware samples, run them in a safe, isolated environment to get a memory dump, and then unleash Yara to hunt for those telltale fingerprints.
So, the big question is, how much better is this memory-based approach in the real world? Well, the data from experiments like these gives us a very, very clear verdict. In one experiment, they scanned 100 different samples of the Amade malware. Traditional file-based scanning, looking at the disguise. It was only able to catch 71% of them. That means almost a third of them just slipped right by. And this is the amazing part. When analysts scanned the memory of those exact same samples, the detection rate shot up to an incredible 95.2%. By completely ignoring the disguise and just looking for the fingerprints in memory, they caught nearly every single one. The difference isn't just big, it's an absolute game changer.
So this is really the crucial point. Why is this method so much stronger? Well, it all comes down to making things incredibly expensive and incredibly difficult for the attacker.
This table really lays it all out.
For an attacker, tricking a file-based scan is cheap. It's easy. They just use a new packer or a different encryption key. The difficulty is low. But to hide from a memory scan? Oh, now they have to fundamentally re-engineer the core logic of their own malware. And that is incredibly difficult and very, very expensive to do.
And here's why it's so hard for them. Trying to hide those core functions in active memory is a technical nightmare. It means rewriting code while it's running, which is massively complex and makes the malware super slow and sluggish. And even worse, these advanced techniques are often really unstable, which can cause the program to just crash. And the irony is, the super complex method they use to try and hide can become a brand new, even easier fingerprint to spot.
At the end of the day, this whole approach forces the attacker into a corner. The effort it takes to stay hidden in memory becomes this unfavorable trade-off, where the cost of trying to hide completely outweighs any potential benefit they might get from the attack.
So, after all of that, what's the one thing you should really take away from this?
It's this. A file on your disk is just a disguise. It's the story the malware wants to tell you. But the code that's actually running in your computer's memory, that reveals the undeniable truth of what it's really doing.
And this powerful technique really leaves us with a final thought about this never-ending cybersecurity arms race. If we accept that a program's true intentions are always visible in its memory, what does that mean for the future of security and maybe even our privacy on every single one of our devices?